This lesson is going to focus on piecewise functions again, but this time writing equations for them. So that's going to be what we look at here. So we're going to be in the Unit 1 Note Guide, starting looking at example 3. So we're going to look at it situationally. So actually a lot of real life situations are modeled by piecewise functions because they might behave one way for a portion of the time and then a different way beyond that and then a different way beyond that. So we're going to look at one of those situations and then we're going to look at them graphically. So this first example, example 3 that we're going to talk about, writing equations, it says a long distance calling plan charges 99 cents for any call up to 20 minutes in length and 7 cents for each additional minute or part of a minute. So we're going to write a piecewise function to represent this situation. So the first thing we want to recognize is that our piecewise equation should have two pieces because there are two different scenarios. So know what your things represent, the different variables. Our y variable, or our f of x in this situation, is calculating the cost and cost of the call, if you want to be more specifically, a long distance call. And then x is the minutes, or the amount of time spent on the call. So we're calculating cost, and what we're going to use as our variable in the equation is x, and x for us is going to represent minutes. So notice they charge 99 cents for any call up to 20 minutes in length. So I get a flat rate for 20 minutes. So the amount of money I owe is exactly 99 cents, not multiplied by x or anything like that, because it's a flat rate. It's not changing with the cost of the minutes. And that is as long as my minutes are up to, meaning the maximum is 20 minutes. That would include 20 minutes. If you wanted to, you could put a greater than 0 on there to make it realistic for this situation on a mathematical graph. But if you, depending on the conversation you had before or the instructions you put with it, it might be understood. So we're just going to write it there to be very pure with our notation here. The second portion says it's 7 cents for each additional minute. You need to be a little bit careful when you're writing these equations. A lot of us want to write down this to represent 7 cents times the number of minutes. But that would calculate 7 cents times all the minutes that you're on the call. But remember, for the first 20 minutes, you're charged exactly 99 cents. So let's think about that 21st minute. What happens when I go past 20 minutes? Basically, I'm charged the 99 cents, and then I'm charged for 1 additional minute. Let's think about when you go to 22 minutes. You're charged the 99 cents, and then you're charged the 7 cents, but you're charged it twice. Okay, what about 23 minutes? You're charged the 99 cents for 20 minutes, and then you're charged the 7 cents, but you're charged it 3 times. So remember, this was when we were using an x value of 21. This was an x value of 22. This was an x value of 23. Notice what's happening in this expression. They all contain 99 cents, and then they all contain 7 cents being multiplied by something. We could put a 1 right here if we wanted. So I know my equation is going to be 99 cents plus 7 cents multiplied by something. And then what is the something? Notice it is not x. If it was x, this would say 21, 22, 23. You're already being charged for your 20 minutes right here. It's only the additional minutes that are multiplied by the 7 cents. So notice that each of these numbers multiplying the 7 cents is the how many minutes you've been on minus the 23 minutes. So if I've been on for 22 minutes, if I take away the 20 minutes that I was already charged 99 cents for, I'd be left with 2. That's what I'm getting here. So what's multiplying the 7 cents is our number of minutes minus the 20 minutes that we've already paid for with that 99 cents. And this is what people are going to charge us for as long as we stay on the phone over that 20 minutes. So when X is beyond 20, that's how we're calculating our cost. So how much would a call lasting 23 minutes cost? In mathematical terminology, that means you're now finding f of 23 for your equation that you wrote. 23 is an x value that's in the domain where x is larger than 20. So that means we want to use the second branch or piece of this piecewise equation and plug in 23 for x. And that would give us kind of what we were talking about as we were just going through it in our head, rationally how we would calculate it. And so we're just going to finish calculating this. And it turns out that f of 23 is equal to $1.20. So that's how we write our equations when we're looking at a situation. You really have to analyze how you're putting together those equations and that you're using the correct restrictions. Now we're going to look at what we would do if we're looking to write an equation from a graph, from a picture that we're seeing here. So when I look at part A here, I'm going to get ready to write a piecewise equation. How do I know to use a piecewise? Notice it's not one singular curve that I've studied before that falls into one specific category. These are all lines, but they're parts of 3 different lines, and that tells me that this is one graph or one equation, but it has 3 different portions to it. So when I look at the first portion, I'm going to call this one on the left the first portion that I'm focusing on. I'm going to go ahead and focus on what would the equation of this line be. And you guys have a couple of different ways that you can do this. You can, if you can identify 2 distinctive points, you can either count from the graph, or you can actually use those 2 points. Like this point looks like -2, -4, and this point looks like -1, -2. You could put them into the slope formula or something like that. What I see from the graph here is that my points are rising 2 and running 1, so that the slope of that line is 2. And then I need the y-intercept. If it's close to the y-axis, you can probably just count backwards as if you are extending the line and see it fairly quickly. I'm going to do it another way in case you guys are encountering a graph that's more difficult or crosses through at a very inconvenient place. Remember that basically right now you know the graph of this line looks like y equals 2x plus b, and you're searching for this y-intercept value. Remember that you can find that by plugging in one of the points. So let's say that I plug in -1, -2. And then I solve for b and I get 0. So the equation of this line is actually going to be y equals 2x plus 0. I don't need to write the plus 0, so I'm just going to leave the equation as 2x. And then I need to put some restrictions on that equation. I'm going to erase this work just so you guys can more clearly see the graph that I'm working on. What are the restrictions? So notice that the graph continues infinitely here, but its endpoint is right here. Remember, we want to list domain restrictions. Domain restrictions mean how are the x values being restricted. So this corresponds with an x of -1, and the points are on the left side of -1, like this portion of the number line. And the point is open, meaning we're not allowed to exactly use the value of -1, but it is where the boundary is. So what I see is that for that line, x values are less than -1. Now I'm going to look at the second piece of this function. It's a horizontal line, and it appears to be crossing the y-axis at 1. So equations for lines like that would be listed as y equals 1. Remember, we already have our y equals in our f of x, so in the next section I'm just listing is 1. And again, I need to analyze the boundaries. So this left boundary seems to line up with a value of -1 on the x-axis and the right boundary +1. Notice that this point is filled in, which means we are including or equaling to the x value of -1, but this one is open, meaning we are not including or not exactly equal to the x value of +1. So x is greater than or equal to -1, and at the same time, smaller than positive 1. Now looking at the third piece of this function, again, I'm going to try and identify some points so that I am able to find the slope of the graph. And remember, you can do that by writing out the points and using the slope formula or counting on the graph. They appear to be going up 1 over 1. So my slope is 1. And then I want to look at one of the points. It appears that I have a point here that's at 3, 2. And plug in those values to see what the y-intercept would be if this complete line was graphed. And after solving this, we should get a y-intercept of -1. So the equation for this line will be y equals x minus 1. I'm going to include that here. And then for the boundaries, the closed endpoint of this graph seems to line up with an x value of 2. So I would say that it corresponds to x values that are greater than or equal to 2. Now looking at part B. Part B is actually a special function, and we're going to discuss it in the next section as well. But this one special function is made up of a piecewise function of 2 different pieces. So hopefully you guys can identify why I'm saying there are 2 different pieces. I see lines, but I see that I would have to write 2 different equations to express those lines. One for the line on this side, and a separate one for the line on this other side. And we are going to consider these continuing lines when they kind of reach the end of the graph like that. That's what they often mean if they don't include the arrows, though I do think it would be nicer if they had included the arrows. So I'm going to look on the left side first at that first line, and I'm going to go ahead and figure out the equation for this line. Notice the slope. So again, you can pick out 2 points and plug it into the slope formula, or you can count it. It seems to be going down 2 over 1. So that would mean that the slope for that line is -2. And then I see that it crosses through this point right here, which is the point -1, 0. And I'm going to go ahead and plug that in to see what my y-intercept would be, or you could see it right on the graph. Honestly, you guys, if you see it right on the graph, I would encourage you just to use it. I'm just going through a process so that when they're more difficult, you have a strategy for what to do. So we get a b value or a y-intercept of -2. So the equation for this graph would be -2x, for this portion of the graph, minus 2. And then I want to look at the restrictions. So I'm going to notice the endpoint here, and that it lines up with an x value of 1. And because this line is graphed on this side, be real careful. A lot of you guys, because the arrow goes upwards, want to say greater. Remember, you're expressing x's. So the boundaries at 1, this line corresponds to all the x's on this side of 1. That's the left side, and those are x's that are less than, since it is filled in, I'll put equal to 1. I'm now going to do the same thing for the other side, or the other piece of the function. So for this one, they're so similar. They're like mirror images of each other. It also has a slope of 2. But this has a positive slope of 2. And I could either continue that pattern to see where this section of the graph will cross the y-axis if it was graphed in its complete form, or I can plug in a point. So I see the point right here that is 3, 0. And I'm going to plug it into that y equals 2x plus b idea to see what that gives me. And that should give me a y-intercept of -6, meaning the equation of this portion of the graph, that line would have an equation of 2x minus 6. So I'm going to put that here. And then I'm going to acknowledge the restrictions. So it stops here, again lined up with 1. They have overlapping endpoints, this graph. This time the points would be on this side of the boundary of 1, which are the x's that are greater than 1. And I'm not going to write equal to because I already wrote it in the other one. So Though you would technically get the same graph, it's kind of unconventional to have both of them equal to 1 if they're overlapping, and that point is already captured.